Today we're going to talk about acid-base neutralization reactions. Acid-base neutralization reactions, as its name suggests, are reactions in which you end up forming a molecular substance in general, but you're mixing an acid and a base together. For instance, take the first example of lithium hydroxide and hydrobromic acid being mixed together. Lithium hydroxide, lithium's a group 1A, so it's +1, hydroxide -1, so it's just going to be LiOH. It's going to react with hydrobromic acid, HBr. Remember, if it starts with hydro, it doesn't have an oxygen in it. It's just H plus whatever that root word element is, HBr for hydrobromic acid. When you mix those two together, you can think of it as flip-flopping the first two elements if you want to. If you notice, what happens is you get HOH and LiBr. Well, what's HOH? It's water, H2O. Now, I like always putting water at the end, so I always put the H2O at the end, the LiBr first. Since Li is +1 and Br is -1, we don't need to add any subscripts. So now let's look and see what ionizes. The Li and OH, Li is a group 1 element. It's going to split. It's a strong base. HBr is a strong acid, so it's going to split or ionize. And since Li again is a group 1 element, it is virtually always soluble. So that's going to split as well, keeping in mind that we want charges on all of these things. So let's write those down. We've got Li plus OH minus plus H plus Br minus, and that's going to form Li plus Br minus plus H2O. So what can drop out as spectator ions? Looks like we're dropping out lithium, the lithium ion, and the bromide ion. And just as we get for every single strong base and strong acid reaction, we get, I'm going to rearrange it a little bit just because I like it better this way, H plus OH minus yielding H2O. If you deal with a strong acid and strong base, you don't have to go any further. You can just write this down and you're done. So look at the next example. We've got gaseous hydrofluoric acid mixed with solid silicon dioxide. So we've got HF, hydro, remember, means it doesn't have an oxygen in it. It's just H plus whatever the root element is. And it's being mixed with silicon dioxide. So we flip-flop the first two elements, and we end up with silicon with fluorine and water, or excuse me, hydrogen with oxygen, which is going to give us our water. Now, what does that do as far as the silicon is concerned? What's the charge going to be on silicon? Well, look at it with the silicon dioxide over here. If oxygen is a -2, then silicon is going to have to be a +4. So let's just keep it a +4 on this side. And since fluorine's a -1, we're going to end up with SiF4. So in this case, what's going to split? Well, actually nothing is going to split. We're going to end up with a weak acid HF and molecular compounds for the rest of them. So all we have to do is balance it. We've got 4 fluorines over here, so let's put a 4 in front here, and it looks like when I do that, not only does it balance the fluorines, but if I put a 2 in front of the H2O, it's also going to balance the hydrogens, and our oxygens balance as well. So that's our reaction for this one. Again, forming water, a molecular compound. So what about the next one? Watch out for ammonia and other amines. We've seen amines before. They act as dirty, nasty hydrogen stealers. So we're going to make sure that we use those dirty, nasty hydrogen stealers when they're reacting with acids. So look at ammonia, NH3. reacting with acetic acid. And personally, I prefer the Chiku form for a sneezy acid. It's also often written as HC2H3O2, but I really prefer it in the CH3COOH form. Keep in mind that the hydrogen here is the same as the hydrogen here. So that's the acidic hydrogen, or the one that's going to get moved around or stripped off when this reacts. So NH3 acts as a dirty, nasty hydrogen sealer, so it's going to form NH4 plus. And what's left behind is just the acetate ion, CH3COO minus. So that's our reaction. Nothing else can further ionize. NH3 is molecular, and CH3COOH is a weak acid, so it's going to stay in that form. Once again, we have to watch for equimolar situations. Equimolar situations mean that we are, again, going to be working with a one-to-one reaction. So let's see how that plays out. We've got potassium hydroxide and phosphoric acid. So we've got KOH reacting with phosphoric acid, H3PO4. And let's see how that's going to play out. If this is a one-to-one reaction, we're going to flip-flop with potassium and hydrogen. But think about it. If we flip-flop with potassium and hydrogen, we can only flip-flop one-to-one. We've only got one potassium. We can only get one hydrogen off. So we're going to end up with our HOH, or H2O. I'll write it here this time since this is confusing enough as it is. But now when we write our K with the remainder of the compound, remember we can only take off one hydrogen. So what's left behind? H2PO4. Now that is a polyatomic ion that we have dealt with before. That's our dihydrogen phosphate. Potassium's +1. Dihydrogen phosphate is -1. So that's the formula for that compound. Again, equimolar means we react one-to-one is the best we can do. So what happens now? What splits? Well, the KOH does because it's a strong base, but what about H3PO4? It does not. It's a weak acid, so it won't split. Of course, water doesn't, but our potassium compound over here with our dihydrogen phosphate will. So once again, make sure we've got our charges. We end up with K plus OH minus plus H3PO4, and it's going to react to form H2O. Our kind of odd K plus H2PO4 minus. And what's going to drop out? Well, of this, the only thing that's identical on both sides are the potassium ions. So our final reaction is going to be OH minus, and it's one-to-one, so I don't have to worry about balancing it. That's the nice thing. Plus H3, PO4. Our hydroxide can only steal one hydrogen away to make the water, and we're left behind with H2PO4 minus. That's our final reaction.